Hello everyone, so in this video I'm going to show you how to draw a Newman projection, which is what we have here. So I'm going to call this a Newman projection from a line and angle structure, okay? Remember, a Newman projection is a projection that is given when we are looking at a molecule through a carbon-carbon bond. So guys, when we are talking about a Newman projection, we gotta be specific and then tell exactly this is the Newman projection when molecule X is viewed through CX-CY bond. Okay, so Newman projection looks like this. This is the front carbon. You draw long lines to show the bonds to this front carbon, and then the back carbon is behind this one, and then you show this line from the border of the circumference to show the atoms or groups that are bonded to the back carbon. Okay, so here is a line and angle structure. Remember, a line and angle structure is a structure that does not show any hydrogens. Okay, so to convert a line and angle into a Newman projection, the first thing that I'm going to do is to convert the line and angle into a Sohor's projection. So Sohor's projection is a projection in which we are indeed showing hydrogens for the carbon-carbon bonds that we are actually analyzing. So in this case, I'm going to draw the Newman projection of this compound when viewing it through C2C3 bond. So we need to name the carbons. Remember how I said, number the carbons, I'm sorry. Remember how I said in class that nomenclature is important for Newman projections, so you have to know when you're numbering the carbons how to number them. Remember, the longest chain gets a number, and then obviously that chain will have two ends, so you will have to make a decision on which end will be number one, and that will be based on the substitutions on this chain, so you always want the substituents to have the lowest combination of numbers possible, right? So in this case, I'm sorry. So in this case, I am numbering the carbons as I just show here, 1, 2, 3, 4, 5. And then the goal of the problem is to draw the Newman projection when viewing on the molecule through the C2, C3 bonds. So I'm gonna write here C2, C3. So everybody knows that that's what we are looking at. And the first thing that I'm going to do is to draw the source projection for C2, C3, just to make sure that we are showing the hydrogens for these carbons. So let me uh, do this now. So this is C2, C3. So as you guys should know at this point, in this carbon we have one hydrogen, because we are talking about carbons that are sp3 hybridized. So they have 4 single bonds. And that hydrogen must be obviously going away from you. So remember, the flat line in these line and angle structures are bonds that are in the plane of the screen. So all these flat lines are in the plane of the screen. Wedge bonds are coming toward you. Dash bonds are coming away from the screen. Okay, so this is a hydrogen for carbon 2, and then in carbon 3 we have this group going away from us. Therefore, there is also one hydrogen here, and that hydrogen, because carbon must have 4 bonds, will be coming toward us. So this is the first thing that I suggest you guys to do whenever you're doing Newman projections, because once again, that's going to help you to avoid mistakes. Okay, so this is C2, C3. So we are doing once again the Newman projection when viewing this molecule through this bond. We have just completed the Sohor's projection, and now what we are going to do is to look at the molecule from the plane of the screen, and then from there we will determine which groups are coming toward us to the right or to the left. Okay, so this is where we are standing. Okay, this is from where we are looking at the molecule. The front carbon is going to be carbon 2. The back carbon is going to be carbon 3. Okay, so in the front carbon, carbon 2, when we look it from here to your right, you will have bromine. So we're going to place bromine here. So one of the things that I just noticed, I'm going to uh, turn this around. So one of the things that I want you guys also to know is the following: the zigzag pattern of the carbon chain. Okay, when we are looking through here, you can see how in carbon 2 this group is pointing down. Okay, so we want to use Newman projection where the front carbon have this group pointing down to. I had it the other way around, so I just uh, rotated 180 degrees to get here. So coming back here, so pointing down, we have a methyl group. So I'm gonna write here CH3. To my right, I have the bromine atom, so bromine must be here. And to the left, standing from here, once again, to the left, we'll have hydrogen. So that will be the front carbon. Then the back carbon has pointing up CH2, CH3. Okay, so the back carbon, which is carbon 3, has to your right hydrogen. So hydrogen is in this here, and to your left it has isopropyl. So isopropyl will be here. Okay, and then this will be just the Newman projection for this line and angle structure when viewing the compound through C2C3 bond. Okay, you can do the same thing from the opposite side and then you will get the same result. Okay, it doesn't matter. Uh, so if we want to do a conformational analysis of this compound, remember that what we would need to do now will be to take this Newman projection and then start rotating one of the carbons 60 degrees to the right or the left, keeping the second carbon fixed. Okay, so for example, I would say um, let's keep the back carbon fixed. Okay, and or let's keep the back carbon fixed, and let's rotate the front carbon. So if we keep the back carbon fixed and we rotate the front carbon 60 degrees to the right, so this hydrogen is going to come here in eclipse. So remember, this is a stagger conformation. The bromine will come here and the methyl will come here. So again, I'll draw here the eclipse conformation. Remember, back carbon is the same, so this would be CH2, CH3. Here we have hydrogen, and here we have CH, CH3 too, isopropyl. So back carbon did not move, so we are rotating indeed the front carbon. So the front carbon now is eclipsed to this ethyl group. So this hydrogen, because we are rotating 60 degrees to the right side, the hydrogen will be here, the bromine will be here, and the methyl group will be here. Okay, so that could be the eclipse conformation. Then next we can rotate another 60 degrees, keeping once again the back carbon fixed and rotating the front carbon. That's gonna take us from eclipse to another stagger. So once again, back carbon remains fixed. Now hydrogen will be coming here in eclipse. Bromine will be coming here, and methyl will be coming here. Okay, so that would be 60 degrees to the right. I'm gonna write it over here just in case you guys want to follow. So we are rotating 60 degrees the front carbon. So we're gonna write here 60 degrees front carbon. And that's what we're doing every single time. 60 degrees we're going from eclipse, from stagger to eclipse. Another 60 degrees we're going from an eclipse now to stagger. Another 60 degrees will take us back to another eclipse. Okay, so in this eclipse now, once again, back carbon is fixed. So bromine will be coming here. Methyl will be coming here. And hydrogen will be coming here. Okay? Another 60 degrees to the right side will take us from eclipse to another stagger conformation, and this stagger conformation once again will have the back carbon fixed, and then in the front carbon we will have bromine eclipse here will be coming here, methyl will be coming here, and hydrogen will be coming here. And then finally, if we rotate another 60 degrees from here, we will go from this eclipse conformation to another stagger. So another 60 degrees from here. We will go to another stagger conformation. In this stagger conformation, we have the bromine here. So bromine coming from here to eclipse, right? So once again, 60 degrees from this stagger is going to take us to eclipse. So bromine is coming here. Methyl is going to be eclipse to the hydrogen. And the hydrogen will be eclipse here. And then guys, another 60 degrees rotation from this eclipse will bring us to stagger. And I want you guys to look at what's going to happen here. So in this stagger conformation, the hydrogen is coming here, bromine is coming here, and methyl is coming here. As you can see, this structure and the first one are the same. So obviously, if you keep one carbon fixed and you rotate one carbon 60 degrees at a time, 6 times 60 is 360, which is a full rotation of a carbon. So you should be expecting to get to the first Newman projection. Okay, so all these are conformations. All these, remember, we call this conformers, and this is what you will analyze to make a conformational analysis. So if we're going to do a conformational analysis, remember the factors to take into account are torsional strain, static strain, and angle strain. Okay, torsional strain is basically present in every eclipse conformation. Remember how, and I will upload another video with this, remember how in stagger conformations, the hyperconjugation effect stabilizes the stagger conformation, and when you go from a stagger to eclipse, that hyperconjugation and stabilization is gone. So every eclipse conformation is hiding energy, and we call this energy torsional strain. So torsional strain is the energy required to go from stagger to eclipse. So every eclipse conformation will have torsional strain. I'm going to define here energy required to go from stagger to eclipse conformation. Uh, then static strain is obviously when there is no room for two groups, so two groups, two atoms or groups smash into each other because the volume of the molecule is not enough to have these two, so that's what we call it. So this is the static strain. So the atomic radius of each of the groups is actually big enough as for not having enough space in the molecule to accommodate these two groups, okay? And then finally, angular strain is just any deviation of optimal bond angle, which as we know for sp3 hybridized carbons is 19.5 degrees. Okay, so as I said before, if we are going to make a conformation analysis, so let's say we are going to first, let's label each conformers. So this is going to be 1, this will be 2, this will be 3. And some of these analyses are not easy. I'm picking this particularly complex example so you guys can see. So here we have the 6 conformers. Obviously, the 7th is the same as 1, so I'm not labeling this. 7 is the same as 1 once again, so I'm not labeling the last one. So to begin with, we know that 1, 3, and 5, because they are staggered, they are lower in energy as compared to 2, 4, and 6. Okay, why is that? Once again, the torsional strain. Okay, so the eclipse conformations, as I said many times before, are just transition states between the staggered conformations. Okay, so the molecules will be mostly in staggered conformation, and to exchange between these staggered conformations, they will go through this eclipse conformation. So we consider this eclipse conformation pretty much transition states between them. So in between, so you could ask now, in between 1, 3, and 5, is there any difference in energy between them? So we can look at these structures. So the largest group here is isopropyl. Okay, so we do have some static strain here between these two and between these two in number 1. In number 3, now the largest group is here having static strain with the methyl and with the bromine, and also the methyl with the ethyl. So this obviously will be higher in energy as number 1. And number 5, you can see again the largest group is now having static strain with the bromine, which is smaller as compared to CH3. Okay, so I would say here that number 5 will be the lowest energy conformer, and then followed by so number 5, once again, why? Because the largest group here, and not only the largest, when talking about the largest, is the volume, right? Isopropyl, the volume is isopropyl is bulkier as compared than ethyl. Ethyl is linear, right? So that's what I'm focusing on, isopropyl. So in this conformation, which is a stagger, isopropyl is gauche to bromine, okay? In number 3, isopropyl is gauche to bromine and to methyl. So definitely here you will have a lot more of angle and static strain. And in number 1, isopropyl is gauche to methyl, and methyl is bigger as compared to bromine. So I'm going to say the 5 is less energetic than 1, which will be less energetic than 3. And then in between the eclipse conformations, we have the isopropyl eclipse to methyl here, isopropyl eclipse to bromine here, and then we have isopropyl eclipse to hydrogen in this conformation, methyl is eclipse to hydrogen, and bromine to ethyl. So from the 3 eclipse conformation, number 6 seems to be the lowering energy, and then followed by that again, these are just transition states conformations. Number 2 has eclipse methyl and isopropyl. Number 4, isopropyl and bromine, and then methyl and ethyl. So these two are going to be very similar in energy. Just because these methyl and isopropyl are the largest groups, are going to say that 4 is slightly uh, lowering energy as compared to 2, but really it's not that relevant since they are both pretty high energy conformations, since once again they are eclipse, and secondly uh, they have 2 eclipse interactions. Okay, so to summarize this, guys, if you want to build a Newman projection, this is a Newman projection. Okay, Newman projections refers to a specific C-C bond. In this case, we drew the Newman projection out of this line and angle structure when looking at this molecule through the C2-C3 bond. Okay, so first step, draw Sohor's projection. Sohor's projection, we show the hydrogens in the carbon-carbon bond that we are analyzing. So this bromine is coming toward us, hydrogen is back. This isopropyl away from us, hydrogen is toward us. Once we have the Sohors, we just draw the proper Newman projection. This is the Newman projection that we are going to use because when we look through here, the methyl group is pointing down, so it must be here. And then to our right is bromine, and to the left hydrogen. Left hydrogen, right bromine. And then on the back carbon, CH2, CH3 is on top, and then to your right hydrogen, and to the left isopropyl. Okay? When doing a conformational analysis, you just rotate 60 degrees. One of the carbons could be front or could be back. The end result is the same, keeping the second carbon fixed. In this case, we kept the back carbon fixed. We rotated the front carbon 60 degrees. So you get 6 different conformations, 3 staggered and 3 eclipsed. And then once we have the 6 conformations, we can make a conformational analysis based on torsional strain, static strain, and angular strain on each of these conformations. By definition, the staggered conformations will be more stable, less energetic as compared to the eclipsed. And then within the stagger and the eclipse, you can make a difference in them based on the amount of static and angular strain that you will find in each of them. So I hope this video helped you guys to understand this, and thank you.